Alright, hello. So here, this is where we're going to start going into mixed integer programming, and I want to start this by introducing the knapsack problem, as you can see in the title. I'm kind of going to do this in the narrative form rather than short form, so please bear with me with that. So basically, the story is that we have this guy on the left. He is a robber, and he has just stumbled. He is going to burgle a museum full of precious, expensive objects, each of which they have a particular weight. So I'll actually write that out in words, in a weight and a particular value. And because the robber did not come very well prepared, he has a knapsack, which is no doubt the core of this problem. So the idea is that basically in whatever kind of knapsack he decides to bring, I'm just gonna draw a granny bag here with a flap because unfortunately my drawing skills are not quite up to scratch. So we'll just draw with the flap here, and that's gonna be our knapsack, which he's gonna carry on his bag. So the idea is that this robber, he wants to steal as much value as possible, but the one constraint, and the classic knapsack problem has only the one constraint in that his knapsack can only hold so much. So the idea here is that each of these items, like say this ruby has like a weight 1, weight 2, weight 3, weight 4, weight 5, and then each of them have their own value as well. So there'll be like, say, for just general sake, we'll say value 1, value 2, value 3, value 4, value 5. And so some other formulations might do this as a cost, or like the price of an item, and so you will kind of just see a very similar structure. So the idea of the knapsack problem is that we want to maximize the value, so we want to be able, because the robber wants to steal as most value, so when he sells it off, he gets the most money, but under the single constraint of the knapsack only carrying so much weight. And so now, what makes this a mixed integer problem is the idea of binary variables. So remember in linear programming, we talked about decision variables, where they are variables of which represent the decisions we have to make to get our optimal solution. So here the question is, what is our decision variables? And here, this is where we introduce the concept of binary variables. So, and then you'll see. So binary variables are basically the idea in which we have variables, in this case xi, which can only be 0 or 1, where basically what happens is that the 0 represents, in this case, whether we take the item or not, and the 1 represents whether sorry, the xi represents whether we take the item or not, where 1 means we do take the item, 0 means that we don't take the item. So you can think of it like as an on or off switch as well. So basically, for each of these variables have a x1, x2, x3, x4, x5, and the idea is that if I say 1, 0, 1, 1, 1, that means I'm taking the ruby, I'm taking the hairpin, I'm taking the aquamarine, and I'm taking the painting, but I'm not taking the metal. So that's effectively the idea of binary variables in that respect. So, and that is in essence actually the only decision variable we actually need to worry about. Both the weight and the value are parameters. They are numbers that we assume we know before we start robbing the museum. So the way we do the formulation of the knapsack problem, as you will see in many different sources, is that fundamentally our objective function is to maximize. We want to maximize the value that we take, or that we steal from the museum. So in this case, the maximization would be the summation of the value of each items multiplied by the binary variable. So in this case, so in this particular scenario, I would write it summing over the I. So this would be summing over the I equals 1 with the n, where in this case, just as a little, there will be n equals 5 because there are 5 items. So in this case, this would be vi times xi. So when you think about it, and it looks like my mirroring software is taking a while to update. So you want to maximize vi. So the summation of vi xi. So the idea is that, say if like you want to expand it. So let's say using the configuration as above, what it would turn out to is that you would get v1. So in this case, because we're choosing x1 to be 1, so that'd be v1 times 1 plus v2 times 0 plus v3 times 1 plus v4 times 1 plus v5 times 1. You can see how the binary variable, where if we say x2 is equal to 0, we're not choosing the item, then you can see we are effectively not adding that value. And so you can kind of see how that summation works. So I'm assuming here you understand the sigma notation of summation. So if not, then I will ask you to brush up on that one. So the constraint, and so in this case there's only one constraint. So the weight, not just the weight, the total weight, of items stolen cannot exceed knapsack capacity. And just for clarity's sake, we're just gonna say knapsack capacity is gonna be C, just as some arbitrary constant. So here the total weight of items stolen cannot exceed the knapsack capacity C, and so the constraint in this case would effectively be so once again we want to use the binary variables again. We only want to include the weights of those items we do steal. So I will write down I will actually write down the constraint first. So there will be I equals 1 up to n, where in this case n equals 5 as before. But in this case, instead of v, we're gonna use the weight. So the weight variable was w. So in this case, this would be wi xi. And then this is going to be less than or equal to C, which is our capacity. If you look at the Wikipedia article, they just speak W, and that's fine as well. So the idea is that effectively, if we expand the left-hand side, according to our byte configuration, where we are stealing everything except item 2. You can see again that if you expand the left-hand side, you'll get weight 1. There'll be times 1. And because xi is 1, and then that's plus weight 2 times 0 plus weight 3 times 1 plus weight 4 times 1 plus weight 5 times 1. So once again, you can see by expanding the left-hand side, I'm just waiting for my mirroring software to update the screen. There we go. And then there's just one more. Sorry. So you can see once again that because weight 2 is multiplied by 0, we are excluding weight 2 from that particular consideration. Now, and so this is effectively the power of binary variables, in that it allows us to include the possibility of just saying, do we include something or do we not include something? And that is effectively literally the only difference between mixed integer linear programming and linear programming. It's just the introduction of binary variables that really allows you to think of that allows you to basically switch things on and off. So you will see that in further mixed integer programming problems that the binary variables can be used in so many different scenarios, and we will go through hopefully a few more common examples of mixed integer programming, and then if we've got time, we'll look at a few more variants of those kind of problems. So until then, I'll see you on the next video.